Today, we'll be talking about intelligence-led policing with Neo4j, and we'll also be introducing a new crime investigation sandbox, as Sabine said. We'll start by talking a little bit about intelligence-led policing, what that means, and then we'll introduce the POL data model, which is a data model we'll be using for our demo. We'll talk a little bit about why Neo4j is such a great fit as a technology for this use case. And then we'll introduce the property graph model, Neo4j's property graph model, and Cypher, our query language, before actually digging into a live demo. We'll wrap up by talking about ways we could extend the live demo into a real-world scenario, because it is limited for demo purposes. And at the end, we'll have time for questions and answers. So first, what is intelligence-led policing? So here we have a very formal definition. Intelligence-led policing is a business model and managerial philosophy where data analysis and crime intelligence are pivotal to an objective decision-making framework that facilitates crime and problem reduction, disruption, and prevention through both strategic management and effective strategies that target prolific and serious offenders. That feels a little bit long to me. So the TLDR is really that intelligence-led policing is an information-based operating model, and it aims to provide law enforcement with strategic, actionable knowledge and a targeted approach to combating crime. So what we're really talking about here is how we can use data, we can use intelligence and information to inform law enforcement decisions. Right? These days, many government agencies, including law enforcement, are under tight budget restrictions. Crime is evolving in many ways due to technology and the changing geopolitical landscape. And so what we're really talking about here is a way to give police forces the tools that they need to be able to make effective decisions based on information and minimize, or I mean maximize the impact of what they can do on their limited budgets. So in terms of benefits of intelligence-led policing, it's really designed to enhance rather than replace traditional investigative methods. You still see police people on the streets, traditional means of gathering intelligence are still in place. This is really what we're talking about here, is enhancing that. We talked a little bit already about utilizing limited resources more efficiently. Ideally, what you would be able to do is have a proactive approach to law enforcement, where you can prevent crime rather than react to crime that's already happened. And you can then evolve your methods by identifying trends and hopefully stopping those trends before they become even bigger problems. And really key to this, as I alluded to before, is giving investigators the same sorts of tools as modern criminals have. Right? Modern criminals operate in a very data-rich environment. They have a lot of very high-tech tools. Police forces, government agencies should have the same sorts of tools to be able to do their work. The question we always get asked when we do this demo is, are we talking about a sort of Big Brother world where the police have all sorts of data and are watching your every move? And that's not really what we're talking about. We already live in an environment where we leave digital footprints when we're on social media, when we're on Twitter, when we're on Facebook, when we're on LinkedIn. I live in London. Here in London and in the UK, CCTV is very prevalent. So when you're in a public space, you could be watched, you could be recorded. And so what we're talking about is giving the police reasonable access to this data to be able to prevent crimes or serious incidents, right? And we're not really here to talk about how much data they should have or what they should be doing with that data, but I think we need to trust that the right laws are in place, the right regulations and frameworks are in place to make sure that law enforcement are only using data that's appropriate and they're using it in an appropriate way. So now we'll talk about the POL data model, which is what our demo is going to be based on. And POL stands for persons, objects, locations, and events. And these 4 types of data really make up the bulk of most investigation approaches, right? So in terms of persons, we could be talking about victims, suspects, witnesses, so on. Objects could be vehicles, if we're talking about a vehicle crime, some other kind of evidence, maybe a weapon, maybe a document, a phone, anything, physical or anything that could exist in association with a particular crime or event. Locations could be a crime scene, somewhere the crime happened, could be a home address, it could be a place of employment, it could be a public building, any sort of physical location. And then an event could be a crime, which is really what we'll be talking about today in our demo. It could also be an arrest, it could be a meeting, it could be a phone call. And all of these things can be related to one another, right? So if you have a person, maybe they own a car, maybe they were in possession of a weapon at the time. In terms of objects and locations, you could have a location where a vehicle was found or recovered. You could have a location where a weapon was found. Persons and locations, persons can live at a location, work at a location, have visited a location. Objects and events, vehicles or weapons could be involved in a crime. A phone could be associated with a phone call event. Locations and events, crimes happen in a location. So what we're looking at here is a very richly connected, highly connected set of data entities that have various relationships to one another. And in terms of use cases that tend to leverage the POL model, policing is a big one that we'll be talking about today, but also the same sort of approach to data modeling could be used for counterterrorism, border control or immigration, child protection and social services, which is part of the use case we'll be talking about later as well. Missing persons, or even offender rehabilitation. If you have someone who's coming out of the justice system back into the wider world, maybe you want to help them to not reoffend, and so you need to understand if there's any people they shouldn't be associating with, any places they shouldn't be going, in order to help with their rehabilitation. And the thing that unites all of these use cases together, it's important to be able to use these systems in real time. There's no point in having to wait a day or two for information about a crime if you're actively investigating it now, or if you could use that data to prevent another crime, right? So being able to be proactive as well as reactive is really key, because the data model in this approach supports both of those things. And it really should be able to generate insights, right? It shouldn't necessarily just tell us what we already know. This person was found with this weapon, this person lives at this address. It should be able to generate new insights. So what can we tell about patterns? What can we tell about, rings of people, locations that are becoming important. So being able to look beyond isolated events and gain new insights to our data by the fact that we understand the big picture. So why Neo4j? Why are we having this discussion in the context of the Neo4j graph database? So Neo4j is the #1 database for connected data. It is built from the ground up as an enterprise-grade native graph database. What that means is, because we're working with highly connected data, as we just saw, the highly connected nature of the POL data model, Neo4j is really a very natural fit for being able to express that information, to be able to store that highly connected information in a database and work with it in real time in a way that other types of databases, like the more traditional relational database model, struggle with. Right? And because Neo4j is designed as an enterprise-grade graph database, it allows us to move up the value chain. So instead of treating data as isolated bits, really being able to connect that data, get new information, new insights from the data and the fact that it's so highly connected, and being able to do that in real time versus a sort of batch or pre-computed method. Neo4j has some very high-profile cases. So the thing I like about the use case we're talking about now, investigative-led policing, is it really demonstrates how technology can be used, to make society a better place, right? We're being used to solve crimes, prevent crimes, help vulnerable people. These are all great things. And Neo4j has a lot of use cases that demonstrate this sort of real-world impact. The ICIJ Panama Papers is a big one, as well as the Paradise Papers. So investigation of data leaks that has uncovered, all sorts of alleged tax avoidance, improper behavior amongst politicians and world figures. NASA also uses Neo4j in a knowledge graph, which helps solve engineering problems, including some engineering problems associated with sending people to Mars. And then, other sort of retail e-commerce type use cases like at eBay, where a knowledge graph is used to power conversational interfaces to the eBay shop. And then more specifically, Neo4j has a lot of use cases where our graph database technology is used in government. So we're really going to be focusing today on point number one, security, law enforcement, but that can also include cybersecurity, and really there's a wide range of other use cases for government, research, environment, planning. So being able to manage large projects, large government projects with a lot of interdependencies. Resource management, supply chain management, being able to make the ordering of parts and the ordering of things for government agencies more efficient, saving money, saving time. So there are lots of ways that Neo4j can be used in government outside of just this particular use case, which we'll be talking about today. So just briefly to introduce anyone who's new to the idea of the property graph model and Cypher before we start taking a look at a real example. It's a little bit different from the concepts of a relational database. With a graph database, we have three main entities, three main ways we can store data. First, we have nodes, and these represent the objects in our graph. So they tend to be nouns. Here in this diagram, we have nodes represented by circles, and we have two types of nodes. We have person nodes, and we have a car node. And so those are labels on the node, just to tell us how we've labeled it sort of as a type. It doesn't necessarily imply a schema. Nodes with the same label can have different properties, different types of data associated with them. We can see that the person in the upper left is named Dan. He was born May 29th, 1970, and we have his Twitter handle @Dan. So each one of those is a property, and properties are just key value pairs. So name is the name of a property, Dan is the value. Born is the name of another property, May 29th, 1970 is another value. You can see the person on the right. We have the name property, which is Anne, and we have born December 5th, 1975. We don't have a Twitter handle for Anne, and that's okay. As I said, there isn't a schema implied here, and we don't have to put a null value in for Anne's Twitter handle like you would in a column in a relational database. Between nodes, we have relationships. So we can see the person on the left, Dan, lives with Anne, and every relationship is stored in the database with a direction. So you can see the direction of the arrow. Dan lives with Anne. Sometimes that direction is important and sometimes it isn't. So if Dan lives with Anne, you don't need to know Anne lives with Dan using a relationship in the other direction, because it wouldn't really be possible for Anne not to live with Dan if Dan lives with Anne. However, Dan loves Anne, and in this case, it is important for us to have the relationship going back the other way, because it would be possible for Dan to love Anne, but Anne not to love Dan. So happily here, they love each other, but that may not always be the case, and so some relationships, it's important to have them pointing in both directions. Loves and lives with, as well as drives and owns. These are labels on those relationships. So relationships have labels just like nodes do. And relationships can also have properties. So you can see Anne owns a car. That node car has a brand value of Volvo and a model of V70. We can also see Dan drives this car, and he has since January 10th, 2011. So you can have properties on relationships as well as on nodes. Those are really the fundamental building blocks of a graph database, of a graph data model. And just with those few key elements, you can make some very rich data models, which we'll see when we get into our demo. One of the benefits of this really is that the whiteboard model of this is actually the physical model, right? So anybody who's had to do very complex data modeling exercises on relational databases will know you often start with a logical data model working with the business or with the subject matter experts, and then you have to go away and normalize that and break everything out into separate tables with join tables between them. And then often the result you get back is very complicated and difficult to understand. Whereas with the graph database, the way you would draw it on the whiteboard is the way that you physically model and store that information, the way you query with it on the way back. So it really can make data modeling much easier, much more intuitive, and really ease that process of defining a data model, both with IT and business folks. This is Cypher, a brief Cypher example. So Neo4j uses a query language for graphs that we've designed called Cypher. It sometimes feels a bit like SQL, but it's very graph specific. So here we have the same nodes that we had before, Dan loves Anne. If we wanted to find out who Dan loves, we would write this query. So match first is sort of like a SQL select. We're looking to match a pattern in the graph. In parentheses, in the rounded braces, we define the details of the node we want to match. So in this case, :person is a label. So we're looking for a person node, not a car node. And then in curly braces, we have the key value pairs, the properties we're looking to match. So we're looking for a person node with a name property that equals Dan. Then we draw the relationship. It's sort of like ASCII art, right? You can see the direction of this relationship, and you can see the label for it. So we're looking for love's relationship that moves from Dan to someone else, right? So just the way we had seen it in the diagram before. And then we're not going to define anything about the person that Dan loves because we want to pull that node back. So again, in parentheses or rounded braces, we just put a variable name so that when the results come back from that query, all the details about that person that Dan loves will be stored in that variable, which we can then work with in a subsequent part of the query. Okay, so with that said, we'll get ready to go into the demo. This demo is actually being run on a Neo4j sandbox. So Neo4j has a number of databases that you can spin up for free. You register, you launch a sandbox. It's good for 3 days, but it's extendable up to 10 days. And they mostly involve data as well as a guide, which we'll take a look at here. So it's a great way if you're new to Neo4j, you don't necessarily have any data to work with or a use case in mind. You just want to get stuck in and start using it. You can spin up one of these sandboxes, start playing with some of the queries, work with some data that's in there. And it's a really great way, with no hassle, no cost, no software to install, just to get your hands on Neo4j and start using some of the data and the queries. So this is how we're going to be running the database today, just to show how that works. In terms of the data for the demo, it will look relatively real. This data set that we're working with was downloaded. There's freely available data in the UK for a street level crime. We're going to be using data from the city of Manchester from August 2017. However, when you download that data, it gives you crime IDs, it gives you a longitude and latitude, at kind of the block level, so it's not completely precise. And they only give you the month. They don't give you a date and a time, and they don't give you any information about people who was associated with the crime in terms of being a victim or a witness or a suspect or what have you. So that information was randomly created and kind of inserted by hand by me. So this certainly, while it may look real, you know, the classic line is, you know, any similarity to real people or events is entirely unintentional. This is a fake data set for demo purposes. In terms of data volumes, we've got just about 15,000 locations in the database, almost 30,000 crimes, 370-ish persons in the database, and a total of 105,000 relationships. So in Neo4j terms, quite a small graph, but for demo purposes, definitely rich enough for us to look at some interesting scenarios. And so, with all that said, we can now have a look. Just to show you what the Sandbox page looks like, this is my Sandbox page. I'm logged in, and you can see here I've got one Sandbox running. I could click, you know, this to launch my browser. You know, there's all sorts of information that's available, and so if you launch a Sandbox, this is what you'll get in terms of an interface. It's really very easy and a great way to get started. When you launch the Neo4j browser, you'll see something like this. So this is the poll model overview. The demo for this particular use case is written step by step in a guide like this. So this diagram will look familiar. We looked at it just before. And as you click through, you know, it's kind of a script that introduces the scenario. And then introduces a series of queries that you can run. So we'll take advantage of a few of these. First, we'll take a look at the data model here. This is the shape of our data. This is kind of our metagraph. This describes all the entities that are in the database and how they're connected. So we can see in terms of the poll model, we have persons here in red. Persons can be associated with other persons by a series of relationships. So we know that they know each other because they live together. They've called each other on the phone. They're family members. They know each other through their social networks. And then we have a catch-all knows relationship that we use as a bit of a shortcut sometimes. Objects, so that we have a generic object type, which might contain evidence or something like this. We also have some vehicles in the database for vehicle crimes. Another sort of flavor of person is officer. So officers can be investigating a crime, or a crime can be investigated by an officer. So crimes is the E in our model for events. We also have phones, which would be another type of object, and phone calls here, which would be another type of event. We have email addresses for some of the persons. A person can be a party to a crime, which for the purposes of this demo is really shorthand for suspect of. We don't have a richer set of relationships here for, you know, to represent who reported a crime or who witnessed a crime or whatever. Persons can have a current address of a location, so that's the L in our poll model. Crimes can also have occurred at a location. And then we have a number of ways that we sort of aggregate locations up at different levels. So we have a postcode. Every location would have a postcode, and we have a postcode node so that we can see all the locations that are in that postcode. And then postcodes can be in an area, and a location can also be in an area. In the UK, postcodes are kind of split into two sections. So for example, M35RW, M3 would be the area, which kind of represents a neighborhood usually, or a small town, whereas postcode is very specific. The full postcode would be specific to a street or a portion of a street. So the postcode is really a very small area, whereas the area is a bigger one, and then you would get city and you know, county or what have you above that. Okay. So now if we flip through some of the general queries that we have here in our guide, First, we can do a basic crime count, right? So we're matching all of the crimes, and then we're returning them as a crime type and the number of crimes that are in the database for that crime type. So a very SQL-like query. You can see violence and sexual offenses has the highest number of crimes in the database, followed by public order, and then moving down, with drugs and possession of weapons at the bottom. We can do the same thing for locations. So if we want to find all the locations where a crime has occurred, and then find the locations where the most crimes have occurred, this is the query. So this we're limiting to 15 results. We can see Piccadilly, which is the main train station in Manchester here in the UK, has a total of 166 crimes for the month. And this is a lot of pickpocketing, shoplifting, bicycle theft, this kind of thing. So perhaps no surprise that the main rail station in town has such a high level of crime. Then there are shopping areas, prisons, nightclubs, lots of public spaces where you would expect perhaps more crime. And it's not until you get down to Walker's Croft or Watterson Avenue where you start to have some more residential looking addresses mixed in. Okay, now we can do a slightly more complex query. So Neo4j supports geospatial searching. So we can search in the graph not just by relationships around a particular node, but using distance. And we can do this because the crime data I downloaded has longitude and latitude values associated with it. So I can convert those longitude and latitude values to a point in space. I can find all the nodes that are within a particular radius of that point, and then I can return those. So here what we're doing, we're having a bit of fun. Coronation Street is a soap opera that's set in Manchester, in a fictional neighborhood in Manchester. There is a Coronation Street address in the database. So we can find all of the areas with crime, or at least the top 10 areas with crime within 500 meters of that address, 1 Coronation Street. So we can see here, 1 Coronation Street actually had 3 crimes logged at that address: bicycle theft, violence and sexual offenses, and public order. 104 meters away, there was a public order offense on Gloucester Street. 162 meters away, there were 3 crimes, a mix of public order and shoplifting at West Crown Avenue, and so forth. Right? So this is quite a handy feature, and especially if you have visualization options that do geospatial visualization, it's quite interesting to be able to combine Neo4j with a geospatial display of the results that you get back from your queries. Then we have a little more fun. So there's another famous television series, Inspector Morse, and there is an Inspector Morse in our graph database here. So we can take a look at all the crimes that are being investigated by Inspector Morse. This might be the sort of real life scenario that you encounter, if you've got a supervisor, or if you are Inspector Morse and you want to log in and see all the things that are associated with you in the database. So we can see here, Endeavor Morse, Chief Inspector Endeavor Morse, with the badge number 57-9485435, is associated with a number of crimes. If we then wanted to explore some of these, we could double click on this, get some of the details. We can see here there's a location associated with this crime. That's 155 Granville Road. There doesn't seem to be anybody associated with that as a suspect, but we can see the details of the postcode and of the area. So on and so forth. So we can not just visualize the results of our query using this tool, which is the Neo4j browser. We can also drill into the data and explore it a little bit more, start expanding our graph based on what we see and what we're most interested in. Okay, now we're going to touch on very briefly, because I don't want to ruin the entire script, the entire guide for anyone who does want to go and spin up a sandbox and do their own crime investigation. There's plenty of scenarios, including some really interesting graph algorithms that we do at the end of the guide. So I would encourage you to log in and play through the whole scenario. But just to step through a little bit of it and give you a sense of what this might look like, we can do a mock crime investigation. So what we've done here is we've queried looking for crimes where the last outcome is under investigation, that are being investigated by an officer with a surname of Larive. So we can see here, Officer Devi Larive has a number of crimes that are under investigation right now, including a few drugs crimes. Right? So what this scenario really does is go into a bit more detail of investigating these drugs crimes, seeing who might be associated with them, what sorts of evidence we have, and how you can use the graph to explore and find paths between kind of arbitrary individuals as part of your investigation. So we'll stop with the guide here, but again, I would encourage you, if this is of interest to you, definitely launch the Sandbox, go through the rest of this guide here, and start to understand how you can use some of these techniques in the graph to find paths between individuals where you're not sure they're connected. We also look for vulnerable individuals in the graph based on their connections who might be associated with crime. And then, as I said, we do also use two separate graph algorithms to look for communities in the graph or highly connected individuals in the graph as well. So what we'll do now, I can show you a few more queries, maybe as a way to expand the poll demo. These are things that are not in the guide, but hopefully will get you thinking about ways that you could write your own queries in the Sandbox on top of the guide. So first, what we're going to do is find locations where a particular series of events have happened. So this is more of a temporal sort of search. We're using time as a factor in how we query the graph. So maybe we have a hypothesis that says, if first we've seen places or events where maybe drug dealers move into a neighborhood, we start to see drugs crime, then we see a wave of vehicle crime, and then the people whose vehicles have been stolen end up being burgled. And so we want to test this hypothesis and see how many times this has happened and where this particular series of events have happened. So first, we look for drugs crimes at a location, vehicle crimes, burglaries, and then we piece this together to say, where the car happened after the drugs crime and the burglary happened after the car. And unfortunately, this query looks a little more complicated than it would need to. This demo and the Sandbox are written against a slightly older version of Neo4j. The very latest version of Neo4j 3.5 includes temporal date and time properties natively, and the operations to be able to work on them. So this query would be a lot shorter and easier to write if it were against the latest version of Neo4j. But we can see here, there are 4 locations that match this particular pattern. So first, we have this parking area. The drugs crime was registered here on the 12th of August. Then we had a vehicle crime on the 15th of August, and then finally a burglary on the 16th of August. So we can see each one of these locations matches the pattern that we described, where we've got a drugs crime first, then we've got a vehicle crime, and then we've got a burglary. And so this would allow us to then dig in, see if there were any other similarities between these locations, these crimes, if any of the same people were associated with these crimes, or maybe this would allow us to then allocate resources to policing these areas, or maybe finding other places where the drugs crime has happened, the vehicle crime has happened, but the burglary hasn't, and then that would allow us to, maybe to allocate resources to that, with the expectation that the burglary was likely to follow. Okay. We can also take advantage of both the time and the fact that we have phone call data. So maybe we want to find crimes where the person who's associated with that crime made a phone call on the same day. Maybe as a way of starting to look at whether or not the person that was called was somehow involved with the crime, or maybe they are someone that the police would want to question. So we can see here, Jessica was party to a vehicle crime on the 30th of August. Jessica has this phone number, and we can see there was a phone call here on the 30th of August. Yeah, and we can see this is specifically because the caller in this case, not the person who was called, but the caller was Jessica, which is how we've written the query. We're only looking for people who were associated with crime who were the caller. If we wanted to find anyone who made or received a phone call on the same day as their crime, it's quite easy to do. All we've done really here is remove the label from the relationship. So it used to say caller. Now we're looking for any relationship there. So it could be caller, it could be called. And so now we have 7 results, 7 phones and 7 phone calls, whereas we had only 3 before when we were looking for just the outbound. For example, here we have Alan Ward. Alan Ward was party to a vehicle crime on the 16th of August. His phone was called on that same date. And then if we wanted to, we could drill into that a bit, look at the person who made that phone call. That was Philip Gardner. And we have a number of other phone calls associated with Philip, so we could use that as part of our investigation to start building a picture of whether or not we have any additional suspects or witnesses here. Okay. We could also look for the person who has received the most calls from persons who are related to crime. Right? So just looking at the database, all the phone call records, who has received the most phone calls from people associated with crime, and that's Paul here. We have his unique identifier, which we're using as his NHS number here. He's only got 1 person associated with crime who's called him, but with 6 phone calls. And so we can drill into that a little bit, find some more information about these phone calls by using his national insurance number here, pulling back the graph. So instead of just a tabular view, looking for the actual graph that sits around them. So we can see here's Paul. Paul has this phone. There are 6 phone calls between Paul and Craig is associated with 2 public order offenses. And again, we can do the same thing if instead of just who's received phone calls from persons related to crime, if we wanted to know who has made and received calls, we can do that now. And we can see the result that comes back is different. So Paul was number 1 before. I guess he's still in the lead, joint lead with Anne, who has 8 calls either made or received from a person related to crime. And so if we want to look at her graph, we can do the same thing. We can see here's Anne. Anne's phone was used in 8 phone calls with Jessica, and Jessica is associated with 5 vehicle crimes. So this might mean that we want to speak to Anne, or at least understand a little bit more about the nature of those phone calls. Okay. So now there's just one more thing I want to show you. So we've been using the Neo4j browser, which is a developer-centric tool. It's great for interacting with the graph, but it really requires you to know Cypher. You need to know Cypher to be able to interact with the graph in any kind of meaningful way. And when you launch a sandbox, the link you get will be to launch that browser. But enterprise users of Neo4j can also have access to a more business user-friendly tool called Bloom. So this is a separate visualization tool really designed for people who don't know Cypher, but still need to interact with the graph in some way. So what we see here on the right, these different colored lozenges, each represent a different label type on the nodes like we saw before. So we have crimes, we have locations, we have persons, and then we have this search bar, which is the main way that you interact with Bloom rather than knowing Cypher. So for example, if I wanted to do the query we did before with Officer Larive and the drugs crimes, I can start typing Larive, I get autocomplete, a recommendation here, then I can type drugs. You can see it's recommending sort of a mini graph here with Officer Larive and drugs crimes associated with that officer. And then that pulls back the graph as we saw before. We can then drill into some of these to get more details. You can see this drugs crime, the date that it happened on. We can see the relationships around that. So without necessarily having to expand all of them onto the screen, we can see some details of where this crime occurred at, who was party to it, what objects were involved. And if we want more details about those nodes, we can look at its neighbors, which are the nodes that sit at the end of those relationships, where we can see a preview of some of that data. So it's a kind of very, it doesn't use NLP, but it is a very natural language-based interface for working with the graph. You can even represent some more complex queries. So for example, where we looked at crimes within a certain distance of Coronation Street, we can do that same thing here. Crimes within 500 meters of 1 Coronation Street. We get the same sort of autocomplete, so 1 Coronation Street and M3 5RW. So the query, the interface, the search bar is interacting with the database, providing autocomplete prompts in real time based on the data that is in the database. So I think maybe postcode wrong is M53RW. So you can see here's the same results that we saw before in our table. These are the locations within 500 meters of Coronation Street, the crimes that are associated with them, and then it's also kind of aggregated up as well with postcode and area. All right, so without having to necessarily write as an individual that complicated cipher where you convert things to points and compare distance, what we've done here is used that same complex cipher in a pre-written query. So if you had a cipher expert who could write that query for you, inserted the variables into that query and kind of hidden it behind a much easier search phrase so that a business user would be able to do the same thing without having to know that cipher. So hopefully that's given you a bit of a flavor for Bloom. And if you are interested in a demo for Bloom, I would say to contact your local Neo4j sales representatives, and they can talk to you about whether or not you might be able to get a trial so that you can try it out on your own data as well. Okay, so that's the end of our demo. We'll talk quickly about how we might extend this. It is a reasonable sized data set and uses some very interesting queries, but in real life, you probably have a richer set of relationships. So we would have suspects, people who are convicted of a crime, who reported it. In terms of locations, you could have somebody working at a location having visited it. You can have owner of a car, you can have driver of a car, so on and so forth. It would be very important to have traceability. So you need to know where your data came from, that you had the right to hold that data, and then limit access to that data to only people who had the right to access it, right? So a robust security configuration would be very important as well. And then perhaps you might want to add weights to this. So for example, some types of crimes might be considered more dangerous, like a violent crime would be more serious than shoplifting. You might weight some relationships more heavily. So, you know, a family member relationship or a relationship between people who live together might be considered stronger than a social network link, something like that, right? And then, of course, you'd load more data. So this is a very small data set, 1 month just from Manchester. You would probably want a whole bunch of information in there, not just maybe crime data, but also perhaps third-party data. You can incorporate weather data, traffic data, you know, anything that might be useful in terms of identifying trends and helping to resolve individual crimes.